landscape, the power of additive manufacturing. And over to you, Devon.
Okay. Cool. Good morning, everybody. Welcome. So yeah, thank you for joining us today, or me today. Well, us, there's some people around here. But yeah, so I want to talk to you about additive manufacturing and how we're applying it into Africa and why it's a game changer in Africa. So to start off, I can't start without telling two slides on the multi-trade story and how it all started. So multi-trade distributors was started by my father 41 years ago. There he is, also running at his father's business, Hanson's Engineering, and he then started multi-trade distributors, and then we found the need. So we sell cutting tools for milling machines. That's where most of our milling machines, turning machines, basically subtractive manufacturing tools, right? And we saw additive manufacturing as an opportunity, as well as a little bit of a threat to that business. So we started in 2019 with multi-trade 3D systems, where I gained a lot of industry experience from Stellenbosch University using their machines, and I'm going to tell you a little bit more about that later. But Africa has some unique challenges, and that especially the manufacturing industry in Africa. Okay, so I want to talk to you about some of those challenges, right? So one of the challenges is skill shortages and low staff retention. So there's many different organizations working on that in this country, maybe even in this place right here today. However, in Greater Africa, on the milling machines and stuff, there's not much of that, okay? But it is one of our issues, especially brought on by COVID. Guys are leaving left, right, and center for higher pay, different countries, going overseas, and that's just one of the issues that we are facing. The other one is supply chain constraints. South Africa is very far from everyone else. As much as we don't like to say it, we're like kind of forgotten here at the bottom. And with that has its advantages. We become self-sustainable, and we are able to do things ourselves and learn about how to do things ourselves. So that's one of the advantages of that, but there are some negatives around this as well. As well as the lack of infrastructure. Okay, I don't have to go on about this one, but electricity is needed for manufacturing. Okay, that's probably the most basic one. There's other things with regards to road transporting of materials. Heavy materials can't fall off trucks when they hit a pothole. So lack of infrastructure is something that's hindering us. If you think South Africa's bad, Nigeria is worse. Okay. But however, the casting industry in South Africa has one of those big problems as well. In the fact, it's really bad, where a lot of the foundries are closing down left, right, and center. The jobs are still needed, the parts are still needed, because casting feeds a lot of different industries in South Africa that are still existing today. Your mining, your automotive, your energy, your agricultural, and the foundries are closing down while we're seeing things like this. So this was on auction, a nice 3,000 kilowatt 3,000 kilowatt, 5-ton standard iron induction furnace. This is in South Africa. Who's going to buy that? You still need electricity to run it, right? So the option is close down, or try to sell, or try to become more innovative, or keep up with technology. 3,000 kilowatts in other countries is a lot more difficult to get on generator power. So this is Nigeria. This is what the casting industry looks like in Nigeria, right? So very manual, burning a lot of things, burning a lot of diesel, burning a lot of processes, very dirty, not very sexy. So you also struggle to get new employees wanting to come into this environment. And that's also one of the issues with casting. Casting is great, don't get me wrong, casting is really good. However, casting is failing at two things: creating new skills and bringing up new guys and training them and trying to make this sexy. And then also sustainability. Casting is also having the issues, especially with power generation and all those other things. So now here's another thing on the milling side of things, right? Another challenge we have in Africa. Where do you get billet stock, right? So if you are going to take billet stock, you're going to cut with a various range of cutting tools. You're going to create a lot of shavings. Where are those shavings going to go? In South Africa, we've got a good scrap industry. Ask the guys on the side of the road. They're effectively working really good at doing that. However, you need a high variability of tools for different operations, and then maybe you can end up with a part like that, right? South Africa, we're still okay, we've still got some things. However, the likes of Nigeria, this is their steel infrastructure. So this is their steel vendors. It's very informal, on the side of the road, you know, very dirty. That's not Nigeria, by the way, that's Europe. And a lot of these are closing down in Europe as well. South Africa is also getting that, right? Africa doesn't have a lot of steel mills anymore. They're closing down. Why? Rising costs, not able to attract people, sustainability, all of those issues. And then it's very difficult to buy billets to machine into parts. Okay? So is additive manufacturing the answer for that? So first, before I go into is it the answer, I want to give you a bit of background on what additive manufacturing actually is and how it can be applied. So when did additive manufacturing actually start? This comics is from 1964. Yes, the applications are highly different to what we're doing today and what we're pushing today in the metals. Batman's scanning Robin and then making a mini Robin. And on that side, they're making busts for the wedding cake or wedding anniversary. Those things have been done. People are doing that, so don't get me wrong, that is an application for additive manufacturing, not necessarily metals. But it looks quite similar to some of the things we're seeing today, especially some of the stuff at our stand. So you can see the arm with the robot type thing, same thing's kind of happening, right? So 1964, the idea was conceived, and now it's somewhat a reality. So what is additive manufacturing? It's the process of joining materials to make objects from 3D model data. This is usually done in a layer-wise fashion, as opposed to subtractive manufacturing. If you look around, you'll see subtractive manufacturing and a lot of it, right? It's got a lot of synonyms, so don't get confused. Additive manufacturing has many synonyms, just like machining doesn't, really. It used to be known as rapid prototyping, but it's also commonly referred to as 3D printing, okay? And this is somewhat what it looks like. Adding layer by layer by layer, bead by bead by bead. Not many people can weld like that. These machines can, and they do it very well. So much so that we don't get porosity, we get better results than castings in some cases. So where does additive manufacturing lie on the bigger scheme of things? A lot has changed over the years. Additive manufacturing has grown from this little rapid prototyping technology to going into different applications, rapid prototyping, rapid tooling, as well as rapid manufacturing. Okay, so getting things fast. Where time is money, additive manufacturing generally wins case by case. So manufacturing is always changing. The subtractive manufacturing market is quite saturated at this point. It's got a growth rate of 4.2% versus the additive manufacturing market is growing rapidly because a lot of people are moving away from castings. GE Additive did it, GE Aerospace did it, and moving more towards your additive manufacturing. And this is growing at a rate of 22% and in fact significantly growing very quickly. So just like you have subtractive manufacturing processes, milling, boring, turning, drilling, broaching, grinding, cutting, all of those are subtractive manufacturing processes. The same is for additive. Additive also has different technologies which are better suited for different applications. Okay, it's very difficult to turn a part on a milling machine. Well, some people do it, but it's very difficult in some cases. So you've got material extrusion, vat polymerization, material jetting, laminated object manufacturing, powder bed fusion, directed energy deposition, and binder jetting. Okay, so these slides will be on the NTA website if you guys do one at a later stage. So at Multi-Trade 3 Systems, we've started looking at the different technologies and which ones are really good for us and really good for Africa, given different applications. So we do material extrusion, vat polymerization. This is only of metals, we don't do plastics. We play with plastics, but we don't make plastics. Powder bed fusion, directed energy deposition, as well as binder jetting. So we have solutions from different companies, different additive manufacturing companies for those different technologies. Just like you have guys that only make milling machines, only make turning machines, only make other things, very similar in the additive manufacturing field. So if you were to make this part that we spoke of earlier, how are you going to manufacture it? You're not going to do it on the lathe, right? It's not the right technology. So you're going to use a vertical milling machine, maybe a 5-axis would be more convenient. So just like additive manufacturing, this part here, a lot of teeth, these are for different patients, very patient specific. You don't have to program each tooth, each G-code for each tooth. It's all done in the software. You're going to manufacture that not with big Meltio, wire-based technologies, but rather powder-based technologies, small little M-Lab, and that's going to be your better option. Okay. So, manufacturing is always changing, so is design. We've got this beautiful thing called AI, right? So AI is slowly incorporating itself more and more into design. Today, you can actually design something with your voice, asking ChatGPT to do it. In fact, there's guys that are going voice to print without touching anything. They're saying, do a cylinder of this size, this size, this size, and please print it for me. And it does it, designs it, and prints it without any interaction. That is where we are now. So, I'm just going to echo what Dave Bullock said about at the last Machine Tool Africa. The design used to be form, what can we make? How can we make it? We can make it with a milling machine, we can make it with casting. Will this part be fit? Does it have the right holes, everything like that? And will it suit our function that we need? In this case, an aerospace bracket. It needs 2 holes there, and it needs 2 holes there, and it needs to hold X amount of weight. But we can make this very quickly with a 3-axis milling machine. Go for it. Okay, but now design has flipped on its head, and we are going function, fit, form. What does this bracket need to do? How much does it need to hold? Where do those holes need to be? What you do is you plug that into the software nowadays. The software then iteratively adds and removes material, does a finite element analysis, and checks if that part will hold up to the weight that is required to by design, with safety factors and everything. And it strips material. It then gives you 20 to 30 options of which part do you think looks the best. All of these are suited for your function. And then you have to manufacture it now. Key holders, machining, it costs money to take material away. Machine time and tooling. With additive manufacturing, it costs money to add material. So you want to add a lot less material layer by layer versus take away material. So we've flipped the value on its head. So like for like, sustainability-wise, additive manufacturing will take machining. We're not machining away, we're removing 90% of the material, turning it into shavings, and then throwing it away. We're adding layer by layer, adding the material only that we need, give or take some supports. So sustainability-wise, it's a lot better, long term. Let's call it 10, 15 years. Speed, like for like, 1 for 1. Additive manufacturing, if I had to print that part versus you, I give that part for you to machine, you still have to order the billet if you don't have it in stock. You have to order the right tooling. You have to get the fixturing. All of those take time. You have to CAM program. I load it into my program, add the supports, and press start. 10 to 20 to 30 to 40 minutes, right? I add the powder that I already have in stock because if I'm printing titanium, I've got lots of titanium in stock and I can make any sort of form with it. And then I go. So like for like, 1 for 1, yes, great. Additive manufacturing will beat subtractive manufacturing in most cases. However, when I say, cool, I want 100, that's when it starts to get complicated. That's when you've already got the fixtures, you've already got the tooling, you've already got the supply chain for your billets, so it starts to kind of weigh up. So it all depends on the applications and what parts you're looking at. Then it is an improved design. Buy to fly, if you're going to buy to fly ratios is how much billet stock are you buying versus what's going in the air. In that case, you're not really buying much versus what's actually in the air, and it's lighter as well. So your fuel, the lifetime of the aircraft, the kilograms per the lifetime of the aircraft is saving your fuel, saving your money. So a lot of guys are pushing to go lighter, and if you're going to try and machine that one, you're going to take a little bit longer. So you can start to not be as competitive. So Airbus, Boeing, all of them are putting these parts in the machine, in their aircraft. So powder bed fusion, just to give you a little bit of background on what that looks like. So most of the parts are small and personalized. Okay, so you can go see that on our stand. You'll see some of the parts there. You'll see really small parts, parts with porosity we've got atomizers, very similar to that. So that is a LEAP fuel nozzle. That's a fuel nozzle in a jet engine. They go around the radius of the LEAP engine from GE, and that is made in one part, no leaking. It's 33% or so more efficient on fuel. So these are and cannot be manufactured through any other method other than additive manufacturing. And then they're often conceptual and sophisticated designs. So very difficult. If I said, cool, that's a titanium part, you're going to struggle to find a welder that's going to be able to do it to the quality of additive. Okay, so that's where additive is really starting to find its niche, especially powder bed fusion. Then we've got directed energy deposition, a different technology, and those parts are bigger and more customized. These weird fan blades, weird impellers out of different materials that aren't really conventionally cast. Low value and low production. So we're not talking about 100. We're not talking about 1,000. We're talking the 10s to 20s to 30s to 40s, depending on what the need is. So that's a nice gap for casting, right? When you go and do a casting production chain, the guys are like, okay, come back when you want 1,000. You can't come back when you want 10, right? They don't want to do the work. Less sophisticated and designs casting, so that's where your bigger printing stuff is actually done. So this is what that kind of... So I've got another video of that I'll show you just now, but that's kind of the process, doing it layer by layer. We've got some videos playing on our stand as well around that. But this is the process chain, this is what it looks like. So you print, technically near net shape, close to billet form, okay? You do some post-processing. You've got to get it off the base plate. You can either machine the base plate off, bandsaw it, wire cut it. You can heat treat that beforehand. In some cases it's necessary, in others it's not. We've got some parts on our stand that have been no heat treating. We've cut them and polished them, no pore, very tiny pores that you can't see in a microscope, as well as we've done some tensile testing, and we got better than wrought in our case, and we did not stress relieve. And then you can do your machining as well. So CNC machining will still be around. You could even put this on a manual lathe and kind of skim it down. So just like the CNC machine was going to be the thing that replaces the manual milling machine, the manual lathe. How many manual milling machines and manual lathes do we have here? They're still here. CNC hasn't replaced it. It's just another tool in the arsenal. Same with additive manufacturing. It's just another tool to make things more efficiently. And then you can cut it off and you can have your final part. So here's just some quick applications for some of those things. Some engine mounts out of titanium. Titanium is very expensive to do it in the first place. So depending on the material, sometimes it's a lot easier to justify additive manufacturing over conventional. Mold cores, cooled nozzles with cooling channels in that go around. You can't do that with conventional machining, conventional casting in some cases. Turbine blades out of Inconel, knee implants out of titanium. Mining drill bits, we've got some on that side. You can now manufacture at the point of need. Injection mold halves, nozzles for the concrete industry. So if you looked at manufacturing, you've now got your printer next to your CNC machine pushing out the billets of different sizes or pushing out near net shapes. So something like this, a 100 kilogram lifting lug, or not lifting lug, U-joint for a train, that can be printed in 200 hours, okay? 200 hours is a long time. The material, the processes are getting faster. Again, there's different processes for different applications. So you don't need your billets anymore, especially in Northern Africa. If you had to say 200 hours, are you going to get a billet in Nigeria of a specific size in 200 hours? No way. Can you get wire in Nigeria? Yes, because welding is actually quite well established in the rest of Africa, thanks to a lot of the South African influence as well. So you can get different billets for different applications, different parts. The material properties in most cases are better than cast, and in most cases very close to wrought, or even better than wrought, depending on the shape, size, and orientation. And then we have reduced tooling. We're no longer doing all that roughing applications. So imagine trying to rough out that U-joint. That's a big machine that you're going to need. That's a lot of tools you're going to need. And if I say it's tool steel or Inconel, good luck, right? It's going to take a while, especially the Inconel. You're going to probably use more tools than the actual weight of the billet itself. And then a lot less scrap, okay? So especially in unestablished countries where the scrap's not as well received, not well handled, you're not getting your pretty penny. You want less scrap. So applications and opportunities in Africa, there's quite a few of them. So I'm just going to go through some that we've been involved in, but also some of the guys here. So over the years, I've been tracking all the additive manufacturing applications or processes or companies in Africa. This is free to go to at 3dprint.africa. You can go and check the map where everything is. You can sort between different types of metal 3D printing facilities, academic 3D printing facilities, and the various types. So you can check that out so you know exactly what additive manufacturing facilities there are in Africa. And you'll see there's some areas where there's not much. So those are the guys who are struggling quite a bit. So applications, tooling industry, conformal cooling molds that conform to the part where you get cooling a lot faster. In some cases, you can reduce your cooling time from 20 seconds down to 2 seconds. Okay, so that means your injection molding tool or machine is getting a part out a lot faster and paying itself off a lot quicker for the small amount that the mold is doing, right? So you can also do printed injection molding, so you can actually pre-print the injection molds, test them, or blow molds in this case, and then see, okay, I like the model, it's great, and then go into production of the mold as well. And then, funny enough, this application on the right is one of the micromilling, somewhat very difficult to find in this country, so the guys struggle to mold the threads. So they just wanted to print these inserts as is, and they were just going to polish the threads by hand, and it worked. So these are the weird applications, unfortunately, that you kind of get. The casting industry, some of the parts I went through, you can see that manifold on our stand as well. This is how it's printed layer by layer. 20 hours of printing time. If you had to try and find anywhere else a skilled welder that's going to actually cut, bend, weld, all of that, it's going to take a lot longer than 20 hours. In some cases, the guys, they'll come to the stand and say, no, we can do this in 2. So I would like to see it, I'd like to put that to the test. But effectively, yes, they'll be very busy for 2 hours, right? The automotive industry is readily adopting additive manufacturing in their processes and productions, okay? So that's BMW, they've just said, they've started producing these wheel arches and stuff and different areas of the motor vehicle for testing before casting, for testing before production, and they said that part is better than what they can currently get off casting. It is qualified, they can use it on an automotive vehicle, and it will hold up to all the stresses of the automotive vehicle through the lifetime of that vehicle. So that is where they're going with that's why ARC, additive manufacturing, that's a form of directed energy deposition. There's me with that fuel, that LEAP fuel nozzle, so there you can see on the actual jet engine, those are flying. So a lot of the GE engines have more than 300 additively manufactured parts that are in the air, and in some cases, the ones that are turning, the turbines, right? Turbine blades are additively manufactured, the low pressure ones on the GE 9A. So it is being used in very unique cases. Aerospace industry, rocket motors, rocket nozzles, satellite components, we've done a few of those over the time as well. In the medical industry, it's being used for implants, so we've just done one medical industry now where they're doing spinal implants in South Africa. Again, that you can manufacture them in South Africa, Nigeria, wherever the hell you want, and that is going to make things a lot easier for the people who are there. And it's scalable, so you need one machine. If your demand grows, you get a second machine. If your demand grows, you get a third machine. So you'll start to see the orange ones were that's the first machine. And then the rebranding happened around 2018. And you can see they started to go blue. So you can see the different scaling of the different machines as they went. Same goes here, retail and online bureaus, printing different parts for different applications. And then refurbishment, repairing existing damaged parts that's difficult to find, difficult to cast. So that one's printed in stainless steel 316L. It's basically repaired just that part. That was in Turkey. This was done in Zambia, on the side. So they're busy scanning the parts, and in that case, if it was broken, they could quickly build it up using additive manufacturing. Back to load shedding would be a lot worse if not for a form of additive manufacturing, right? So these parts of the turbine blades were grown up on using that technology from the CSR, layer by layer, using a powder technology. It's laser metal deposition. It's basically using powder, laser metal deposition. They also draw up labyrinth trails. They do a lot of different things. So CSR is also quite clued up with some of that. Refurbishment of existing parts, damaged parts, creation of spare parts on demand. You need to print it, you can store a digital file. No longer do we need these large inventories of parts. You basically proof it out, qualify it, and then you have them on demand. You say, okay, well I know this part takes me 2 days, 3 days to print, so I just need to have a rolling stock or lead time of 3 days for those parts. This was a conveyor part on the mines that basically failed. And this is a use case again in Turkey where the guys are basically building them up layer by layer. So you could also build it up in a day or two, put it back into service rather than waiting for a large billet to get to the place and then still the shoot down. Mining bits, you'll see the mining bits on our stand. These are consumables. They can be manufactured at the point of need. So you can really actually start to change the game on how this is happening. You can buy in different grades of tungsten carbide billet buttons, and effectively you can adjust the machine for the rock that you're hitting. So if you're drilling and you hit different rock and it wears down the buttons, you change the grade and you print a new one. And 20 hours later, you pop in a new one. If you're in a remote place of Africa, these are the type of things that can really start to change the game on supply chains as well. The oil and gas industry, we're doing some stuff with Shell as well. In Nigeria, they struggle to get parts. In fact, they're struggling to get the 3D printing machines into Nigeria. It's taking 3 months, stuck in customs. So you can imagine how difficult it is to get parts there. So what they're doing is they're putting the machine there, sending a ton of powder, and effectively they could make maybe 500 kilograms worth of parts in a year. They just have to keep sending a ton of powder every 3 months or 4 months just to keep up with that. So they're now additive manufacturing at the point of need or at the country of need, just to bypass that customer, right? So just some conclusions or takeaways. Africa needs to use additive manufacturing more effectively. So fixing power generation issues, right? Creating our own drill bits on site at the point of need. Creating our own automotive components, design, manufacture, whole process chain, as well as repairing and refurbishing our parts on site for the applications. We're going to save a lot of money rather than getting them remanufactured or manufactured again. So this is effectively remanufacturing or refurbishing. So you can also build up wear sites as well with these technologies. Africa needs more additive manufacturing facilities. So this is the facility in Stellenbosch University. That machine is 13 years old. You might not know about it, but this machine actually saved a lot of people's lives during COVID. Those little mold parts there are actually the core inserts that have conformal cooling channels that were used in the ventilator, the South African ventilator, that was developed, designed, manufactured in South Africa. Those are the mold cores for that. So a lot of people actually didn't even know this. I didn't even know that it went there. We just got sent parts. We made them during COVID, and that was still when I was at Stellenbosch. And effectively, those parts were saving a lot of lives. That machine is 13 years old now, still able to push out parts. This one was in Durban, and they were doing also injection molding, conformal cooling channels, and this is some of the stuff. Effectively, we need to start using these facilities, training guys in these facilities. So collaborations, training, everything, we're happy to collaborate. We've got our own technologies, we've got partnerships. We just want to get more additive manufacturing directly into South Africa. And then my favorite one, Africa must not fall for the pretty boxes and the fly-by-nights. You'll be sad to hear how many additive manufacturing machines are in the continent that are covered in sheets, still in the box, not working. There's one in the middle there, just down the road. So a lot of these things are actually problems because guys are selling these, I call them box droppers. They literally drop the box and go. This is a hard technology to understand, right? So there's a lot of people that are selling the technologies. That's a box on the left there, at a trade show just like this. They're showing this technology, developed in Australia. You'll never see that machine anywhere in the world. It does not exist. The technology inside never existed. They showed a pretty box and fooled the masses. It's a publicly funded company. So they're taking retired people's money in Australia and doing this kind of stuff. So this is a new technology. There are a lot of fly-by-nights, guys claiming that they know additive manufacturing. Guys, literally, I've see them every day. I track them. There's guys in Nigeria signing partnerships with guys and doing all these weird things and claiming they have metal machines. They don't have a metal machine. There's many guys that, if you want to do due diligence, ask them for pictures of them by their machines. Ask them to come and see their machine. You'll often see some plastic printers in the place, and they don't have the equipment. So, yeah, it's a big challenge that we're fighting against. And again, use the right technologies for the right application. There's many of them, but these guys come talk to us. We've got a stand over here in the corner behind me. If you need any help, any assistance with additive manufacturing, please let us know. Are there any questions?
Anybody have any questions for Devin? I can see Devin is extremely passionate about his subject, which is great.